Hi everyone. So we start the class. Do you have any questions on midterm? No. So you have 3 questions, and in the last question, you are supposed to use the data set in an Excel file, and you need to modify a little bit to read it to R, because it has basically 2 rows for headers, but the R basically allows only 1 row as a header. So maybe you can eliminate the first row or second row to read the data correctly. Yeah. Question 1 and 2 are more traditional questions, and the 3 is a kind of a data competition type question. So I ask you to do some base models. Then after that, you're asked to search for a better model to fit the model. So I did some experiment and the trial and error to get better model than the base models. And if you beat my model, maybe then you can get a little more credits. Okay. Okay. So no questions so far. Midterm is due on Friday at 11:59 p.m. So if you have questions, ask before that. And today we want to continue to do the chapter 6, the part, section 2, the Lasso and rich regression. And after that, I discuss how to implement the rich and the Lasso in R. Then hopefully that we do some exercise on the Lasso and rich regression. So exercise is available on the website, and also data sets. The Abalone 1 and Abalone 3 are available on the website, so you can download. Okay, so I will at first finish some slides. So last time we studied Lasso and rich regression. So what's the difference between the least square regression, the usual linear regression, and the rich regression or Lasso regression? The difference is here. So least square regression, the linear regression, minimize the residual sum of squares. But the rich regression, they minimize RSS plus the lambda times the norm, Euclidean norm, the square of the Euclidean norm of beta. So that means that we penalize the size of coefficients. So if the many parameters are large in absolute value, that we penalize it. So that we choose reasonably the simple model. So that's the idea. And here lambda is a constant. So we are going to choose some lambda, but the lambda is just a given constant for now. And this is the rich regression, and the Lasso is a similar model. Only the difference is this penalty term is the summation of absolute value of beta j. So it's slightly different, but they are very similar. And the Lasso and rich regression generally are much faster than linear model with very large number of parameters. the idea, for example, for Lasso is that with this penalty, we only have the few parameters which are non-zero. So we start with the smaller model, and we introduce the most significant variable at that time, so that we don't really have to explore all possibilities. So the idea is similar to forward selection. So the forward selection, we start with the the null model, the baseline model with only intercept, and we add one variable at that time. Then we continue until the AIC that does not improve. So that means, suppose we have the 1000 the candidates of variables, and we start with the null model, the baseline model with only one parameter, and after that we introduce one predictor and we add one predictor, and suppose that we finally get the model with 10 parameters. So that means that we only have to fit the model with 10 variables. So that means that we have to calculate, for example, the inverse matrix of 10 by 10 matrix. That does not take much time. Right? So even if the selection process is somewhat, selection process takes some time, but it's much faster than just fitting the model with 1000 parameters. If we start with a null model, the smallest model, and we increase the number of parameter one at a time, and we stop when it does not improve, then it's much faster than just fitting one linear model with very large number of predictors. And the Lasso, since the final model is not large, that we have some algorithm which is faster than a linear model with the many predictors. So elements of statistical learning, which is the slightly more difficult textbook than this one. This explains how to estimate the Lasso, and which is actually faster than the linear regression with many parameters. And the rich regression, yeah, actually, I don't really know the most efficient algorithm for rich regression, but as far as I know, the rich regression also has the similar algorithm which can estimate the parameters fast. I don't exactly know how algorithm works, but actually it's also pretty efficient. So this is another advantage on which model is the best to select. To choose the best model. So in recent years, the algorithm is more important than before for statisticians. Before, statisticians only think about models, like we consider this Lasso or the rich regression, and that's it. And the computation is done by programmers. But now the algorithm is more important. So if we have many predictors, what's the most efficient algorithm? Most efficient statistical model to estimate the model. Yeah, so, and remember that the lambda, we have the parameter lambda. Lambda gives the size of penalty on the size of parameters. So lambda is larger, estimated parameters are smaller. And for Lasso regression, for Lasso, if lambda is large, only a few parameters are non-zero. And here it explains how parameter changes depending on the value of lambda. So lambda is larger, then estimated coefficient is smaller. So this x-axis, horizontal axis, is the size of lambda, and the vertical axis is the size of estimated parameters. So if lambda is 0, basically that's a linear regression, and many parameters are non-zero. You can see maybe 10 parameters. But the lambda gets larger, only a few parameters is non-zero, and the other parameters are also smaller. And this is another way to express the result. So if lambda is larger, the ratio between the Lasso parameter and the linear regression parameter gets smaller. So basically, the large lambda large lambda, then we have smaller estimates. So basically this and this are almost the same graph, but the result is presented in a different way. Yeah, so the Lasso has more parameter estimates equal to 0 because it has relatively larger penalty when beta is closer to 0. So this explains why the Lasso choose this is another explanation on why the Lasso choose more parameters equal to 0. Yeah. And now that we discussed how to decide lambda, so this is based on the simulation results for rich regression and the Lasso. I think which one? Yeah. So this is the case that the true model with many non-zero parameters. So that means the rich regression is probably better than Lasso. And the left graph, you can see that the test MSE here, and this is size of lambda. And this is which one? Not sure which is, I think probably it's Lasso. So Lasso parameter is Lasso model performs best if lambda is about maybe maybe a little more than 2, maybe 3, 4 or something. It's the best. And since this is a simulation, that we can decompose this total test error, the purple one, into 2 parts, green one and the black one. So green one expresses the variance of the model, and the black line that represents the squared bias of the model. If the model is simpler, lambda is large, model is simpler, so it has larger bias. But since model is simple, the variability is smaller. So if lambda is smaller, then we have more complicated model. So bias is small, so black one smaller, but the variance is larger. So model is more unstable. So the summation of these 2 kinds of errors is optimized at some specific lambda. And the right-hand side, we see the comparison between rich regression and Lasso. Rich regression for dotted line and Lasso for solid line. And since the truth has many non-zero parameters, the rich regression has some advantage. So if we fit the model, we can see the rich regression performs slightly better than Lasso. And this is another example with only a few non-zero parameters in the true model. So Lasso should perform better. And we can see that this is solid line for Lasso and rich regression for dotted line. And this Lasso performs better than rich regression here. So the Lasso and rich regression are different models. And depending on the truth, the beta model is different. And this is a smaller, the simpler example to demonstrate the difference between Lasso estimates and the rich estimates. So model is yj is equal to beta j plus epsilon j. This is a little bit strange model, beta j. Yeah, maybe the to estimate parameters, we need the multiple measurements for each j. So, but that's sorry, that's fine. So if we estimate the linear model, basically the estimated epsilon is 0. If linear regression, usual linear regression, okay, so just the beta j explains everything about yj. Of course, we have n parameters for n observations. So basically the yi, so the beta j hat is equal to yj, and the epsilon j, estimated epsilon j is equal to 0. So that's simple. But if we fit the rich regression or lasso, that we have penalty on beta j. So not necessarily the beta j hat is yj. So suppose that the y1, y2, y3, and y1 is 10, and the y2 is 15, and y3 is equal to 5. And what the beta maybe, so it's possible that the beta 1 hat is equal to 10, beta 2 hat is equal to 15, beta 3 hat is 5. But in such a case, we have penalty on this. We have penalty. For example, in the case of Lasso, the absolute value of these 3, so this is penalized. So we have this penalty. So the model has some incentive to make these estimates smaller. So maybe the 15 becomes 13, and the 10 becomes 8, and the 5 becomes 3, or something like that. So we want to see how beta j's are different. Estimated beta j's are different for Lasso and rich regression. So here are the estimates. So this is the value of yj, and this is the estimate, so beta j hat. And if we do linear regression, just yj is equal to beta j hat. So you can see that the estimated parameters are exactly equal to yj. So this is just the line, beta j is equal to yj. And how about the rich regression? Rich regression, that we penalize the parameter. So estimated parameter shrinks towards 0. And remember that we have square penalty. So that means if estimated parameter is larger, the bias is larger. So we make absolute value of beta j hat smaller for rich regression. Penalty is larger for large value of beta j. So you can see that the this shift is much larger than, for example, this shift. Rich regression, that we penalize the summation of beta j square. So if beta j is small anyway, that we don't really have to change beta j much. But the estimated beta j is large, then we have to make it much smaller, not to be penalized. And the Lasso, the penalty is summation of beta j hat, beta j absolute value. So for any value of estimated beta j, we have the constant shift. Of course, beta j is smaller than some value. We cannot, we don't really have to shift by more than the size of the estimated parameter. So, this one maybe smaller shift. But basically, from some certain point to certain point, estimate shrinks to 0. And after that, outside of this range, basically all parameters, estimated parameters, get smaller by a constant amount. So this is Lasso. So in rich regression, if we have non-zero estimated parameters, in least square, in rich regression still, that we have the non-zero parameters. Lasso, if the estimated parameter is between negative 0.5 and 0.5 in this case, then estimated parameter shrinks to 0. Yeah, so these are the characteristics of rich and Lasso estimates. And next one is the Bayesian interpretation. Have you studied any Bayesian statistics before? Bayesian estimation? I think that some of you have taken Stat 5800, and it discusses Bayesian statistics. Or possibly if you have taken 7810, it discusses Bayesian. So
I've done a little bit, yeah.
Yeah, 5800 still covers a little amount of Bayesian statistics, I believe. So they use John Rice's book, right? Yeah, but maybe it's new if you you have taken only 50-30 or 20-10. And Bayesian statistics assumes that the parameters has prior distribution. So we have the two schools in statistics. So one is the frequentist, and the other is Bayesian. And the frequentist think about the parameter as a constant. We have the parameter beta, we have the truth. Then we estimate the parameter by beta hat. And the Bayesian approach is different. So we don't know the parameter. So we have some, prior distribution of parameter. So we have beta. Maybe beta is maybe has mean 0 with the variance 100 or something like that. So this is the prior distribution. We can say that therefore beta. Then after we observe beta, we are more confident about the size of beta. So after we observe data, maybe the beta is centered at 5 with standard deviation of 2 or something like that. So originally we don't have much information. So beta is probably between -10 and +10. After we observe the data, okay, beta is slope, or slope for between y and x is probably between 3 and 7. It's more likely to be around 5 or something like that. So this is called posterior distribution. So this is the Bayesian way of thinking. So this is somewhat easier. I mean, they're more straightforward to interpret, right? So we have some uncertainty before observing data. After observing data, still we have some uncertainty. But we have less uncertainty. And in terms of Bayesian statistics, we can interpret the penalty lambda times the summation of beta j square as the prior distribution for beta. So suppose that for example, beta follows normal 0, 1. Then that means the prior distribution of beta is equal to 1 over square root of 2 pi times the exponential of negative beta square over 2. Right? So maybe log of f beta. Usually we take logarithm to evaluate the likelihood function because product becomes summation, and we can apply some law of large numbers, central limit theorem. And then we have some constant minus, maybe, okay, so negative log likelihood, then plus the beta square, right? Maybe over 2. So you can see that the beta square is the negative log likelihood function. So penalizing beta square is equivalent to the having prior distribution for beta. So in terms of Bayesian statistics, basically we assume the prior distribution for beta. So prior distribution is this. So if estimated beta is very large in absolute value, we penalize it. If we have this prior distribution, beta is equal to 100, is very unlikely, so we penalize it. So in terms of this Bayesian interpretation, the rich regression is equivalent to assume the normal distribution for beta. Normal prior distribution, so normal prior. Maybe we have multiple parameters, the beta 1, beta 2, up to beta p. So maybe I would say that the p-dimensional, the normal prior for beta 1 to beta p. And for Lasso, we have the penalty on beta j as the absolute value of beta j. So yeah, basically the Laplace prior or double exponential prior for beta j. So that we have Bayesian interpretation for beta. Yeah.
So maybe a dumb question, but is there some proof that they use for this, or is it just kind of like a logical reasoning? We use normal for this and Laplace for this. Like why? I guess. Is it just some sort of thinking?
The Bayesian statistics prior distribution don't have much theory, so you have to set something. And the basic idea is that the prior distribution is not very important. So just we have just set our weak assumption. For example, that we set the prior distribution as normal distribution with very large variance. Then anyway, the data adjusts to the distribution of beta j, so it should be fine. So basically the prior distribution that does not affect the final results. That is the Bayesian's concept. So yeah, the answer is we have no theory behind it.
Okay, that's cool.
Yeah, but one thing we can say is that we don't really have to use the ad hoc argument to beta j. So if you observe the data and you optimize the prior distribution, then the result looks better, but we shouldn't do that. So we just set prior before looking at data. So that's the fashion. When I studied statistics in PhD program in Wisconsin, my friend is in the business school in the University of Chicago. And even though statistics department at Wisconsin doesn't require Bayesian statistics, but in Chicago, even MBA program requires Bayesian statistics in the first year. What's the reason? Because the Bayesian statistics, if we set prior, then we can deduce any conclusion, even if data are not reliable. If we set the prior distribution better, then we can claim something. So that's why the business school in Chicago, University of Chicago, that requires Bayesian statistics. So maybe it's useful to manipulate the data. Yeah, but no theory behind it. That's the I think at least frequentist view of Bayesian statistics. Yeah, so as long as it's not ad hoc, that's fine. So just any other questions? Yeah, and yeah, so the prior, you can see that the maybe, okay, so normal 0, 1, the prior is this, but suppose that we have the normal 0 sigma square, then we have sigma square here and a sigma square here. So basically sigma square over 1 is equal to lambda. Maybe 2 times sigma square is equal to lambda. So that means the lambda was the the size of penalty in Lasso and ridge regression, but it can be interpolated as the inverse of variance in prior distribution. So variance is larger, that means the weaker assumption in prior distribution. So sigma, so weaker assumption, prior assumption. This is the large lambda, large sigma square, sorry, large sigma square, and that means the small lambda. So we have this correspondence. And how to set this lambda, how strong our prior view is. And we cannot really set it. The Bayesian statistics doesn't have any theoretical background for prior distribution. So how to choose lambda? Lambda that we can choose by the cross-validation. So for different lambda that we estimate Lasso models, then we choose the best one in terms of test error or cross-validated error. Yeah, so that's it. And this is the lambda value and the cross-validated error. So in this case, the optimal one is maybe here. And the estimated parameters are here. So probably this is close to least square regression. So maybe the parameters will shrink a little bit, but not much. And also, I would like you to care about this scale. So this is exponential scale. So this is the 5 times the 10 to the power -3. So that means the 0.005. And this is 0.05, and this is 0.5, and this is 5. So that means that if we have changed the lambda a little bit, for example, 0.5 to 0.6, usually it does not really matter. Even 0.5 to 1, it doesn't change the result much. But if lambda is 10 times larger or 10 times smaller, maybe results are different. So it's not that sensitive. So lambda, I mean, the result isn't really sensitive to lambda. Yeah, so that's the basically the theory for Lasso and rich regression. Any questions? Okay, so now that we do lab session. So I'm using the R console to explain it. Chapter 6 have the 2 lab sessions, lab 2 and lab 3, and then we do lab 2. We do lab 3 after we finish other materials such as principal component regression. Okay, so you can open the lab chapter 6 lab 2 file. You can see all codes. Yeah. Yeah, so I think you now see my R screen. Okay, so maybe at first I set the working directly. Maybe it may not be necessary. And the library ISLR, so this is for data. The baseball data we are using. And the Lasso and rich regression, we use the GLMNet package. And also we do cross-validation on GLM. So we use this. And we have hitters data. Maybe you can see. So we have the baseball players data at the bat. So this is the number of times the players is at the batting box. Number of hits generated, number of home runs, and number of runs. RBI, what's RBI? The run. Anyone who is knowledgeable about baseball, and the number of walks and years that they played in the maybe MLB. Yeah, actually, I don't really understand all the statistics, but some others. And yeah, and here, since statisticians like money, we want to predict this salary. We want to explain this salary by other variables. I think these are just for the same year. So the salary for some year and the performance in the same year. So it's not really predicting salary, but just explaining salary or something like that. But we want to explain this salary by the other variables. So that is our objective. But actually, these data have some NAs. So far, I cannot really find NAs, but the hitter at about maybe hitters. Maybe this variable hitter doesn't have any.
Right, salary.
Salary have some missing. Yeah, maybe. Maybe I can just say. Maybe is.na. Yeah, we have the 59, the missing. So I don't know how many rows, the number of row of hitters. We have 322 observations, but the 59 of them are missing the salary. We can say maybe header, maybe we can just show everything. So we have the 59 NAs. So, and maybe some other variables also have NAs. So we want to exclude any line with at least one NA. So if one variable is missing, we cannot use that observation for regression analysis. So we want to omit this. So we want to use the NA.omit function. This is very convenient function to omit all NAs. Omit rows with at least one NA. Then now hitters only have 263 lines. Yeah, actually maybe only, yeah, only maybe the salary has NAs. Yep, but it's useful when the multiple columns may have some NAs. And okay, so yeah, and we prepare just all predictor variables except for intercept. So we make this model matrix, so the data set for predictors. So this is salary on all the other variables in hitters data set. And the model matrix includes the intercept in the first column. So we want to exclude it. So the data matrix without intercept. So this is X, maybe header X is, sorry, maybe it's good to have it capital letter. So header X, sorry, header, couldn't find header. Yeah, so these are the first 6 lines. And the Y is the, response variable. So this is salary, so hitters. Yep. So, yeah. So now hitters have just the 20 variables, 263 observations. And now we want to fit the rich regression. And we want to optimize lambda. So we want to set the possible values for lambda. We set 0.01 to 10 to the power 10. So we try these 13 numbers as possible value for lambda. So remember that the result isn't really sensitive to the small difference in lambda. So just I make the exponential function. So we try 0.01, 0.1, 1, 10, 100, 1000, up to 10 to the power 10. And rich regression model, we name it as the rich.mod. We use the GLMNet function and xy. X is predictor, y is response. Alpha is equal to 0. Alpha is equal to 0. That corresponds to rich. So basically, this is alpha. So rich regression. Yeah, maybe for now, just the alpha is equal to 0 means rich regression. And lambda, we try multiple values. These are 13 values. Both capital. Yeah, so rich regression model and a plot rich mod. Then we can see that the estimated parameters for each variable. We cannot really see the which variable is which, but this is the result. L1 norm. So if coefficient L1 norm. Yeah, so this is the estimated coefficient, the y-axis, and x-axis is actually the L1 norm. So I think it's the total of the summation. Yeah, I think this is a little bit, this is a glitch. So basically this is the sum of the beta j square, sum of beta j square. Probably this package was originally made for Lasso, so that's why we say L1 norm, but this is rich regression, so this means L2 norm, I believe. So it's not really the lambda value itself, but if lambda is larger, the total L1 norm is larger. So basically lambda is larger if we go to the right and go to the left. Sorry, the other way around, sorry. The lambda is small, then L1 norm is larger. So the lambda is small to the right, and to the left, lambda converges to infinity. So estimated coefficient is the 0. Yeah, yeah, I cannot really see which one is the which variable. Maybe we have to figure out how to get this legend. Yeah, and also we tried the 13 different values of lambda. So we want to see the coefficients for each lambda value. So we can get that by coefficient of rich regression dot mod. That's the since the numbers are so too many digits, that we just round this to 2 decimal. I mean the 2 digits after the decimal place. So this. Then we can see this. So this is a little bit confusing. The first one corresponds to the largest lambda. So lambda is equal to 10 to the 10th power. So we put the lambda values in increasing order, but this just the reverse the relationship. So this is for the largest lambda for the first column. And the first 3 columns, actually all estimated parameters are 0 because lambdas are extremely large. If lambda to the power 10, so lambda to the 7th power, the one variable, the division W, so this is a slightly negative coefficient. And lambda is 10 to the 6th power, 5th power, 4th power, 3rd power, 2nd power, 10, 1, negative, the 0.1 and the 0.01. So 0.01 lambda is small, so coefficient is much larger. If we set lambda is equal to 0, then we get just the least square estimates. So you can see that the estimates are larger in absolute value when lambda is smaller. We have many predictors, so we have many coefficients. Of course, sometimes it goes in a different way. Maybe here, the runs, the coefficients gets larger from here to here, but probably this is because some other coefficients gets much smaller, such as hits. So that's it. Yeah. So you can see all estimated coefficients for each lambda. Yeah. You can just output what's the lambda value and what's estimated coefficient. So actually the 7th lambda is the 10,000 and 8th lambda is 1,000. So you can see the order has been reversed. Originally we put in increasing order, lambdas in increasing order, but now decreasing order. Okay, and which one is the best? We will discuss it later. Okay, so for now, that we can see that the sum of the squared coefficients. So, for example, for 7, the lambda value of 10,000, that we can get the coefficient of rich regression. We exclude intercept because usually we don't penalize intercept. Sorry, the summation. Sum of coefficient of rich model, and we exclude intercept, and we pick up the 7th column. So the estimated coefficient for lambda is equal to 10,000. Then, sorry, there's something wrong. Maybe one redundant. Yeah, so 52. If lambda is 1,000, the estimated coefficient is the 2,137. So smaller lambda, smaller penalty on large parameters. So the parameters gets larger. So this is squared, sum of squared parameters. So it's a little bit exaggerated, but you can certainly see that smaller lambda, the estimated coefficients are larger.
Quick question. Yep. Maybe
Sure.
You said this already and I missed it. When you say intercept, exclude the intercept, what does the intercept mean? I guess is it the
no intercept is
column?
Yeah, I mean in a linear model, the y is equal to beta naught plus beta 1 x1 plus up to beta p xp, and the beta 0 is the intercept.
Okay.
Yeah. So in terms of data matrix, this is just a column of ones.
Okay, got it. Okay,
yeah.
Makes sense. All right, thank you.
Yeah, and yeah, also the yeah, also if you want to specify just a specific lambda, maybe not really 1 or 10, but maybe 5 or the 4.6, or if you want to pick up the specified specific lambda, also you can use the predict function with S option. So rich model, and we modify the lambda, but here we use S. I don't know, just this is how predict function works, and type is coefficients. Yeah. This isn't really important. If we don't put this, just it outputs as the 20 by 1 matrix, and here just the list of 20 numbers. So almost the same result, but we can specify S. So S is lambda. Then we can get estimated parameters. For example, if we specify S is equal to 100, then we get these parameters. For example, intercept is 2.06, no, the 20.68, and the at bat is the negative 0.115. And these are the same number as we have seen here. So this is one, I think that is, sorry, I have bad memory. Intercept the 20 at bat, negative 0.115, and the intercept is 20, yeah, so here, right? So this is the lambda is equal to 100. You can see that the 110, 0.1 for lambda. So you can see that this result exactly the same as the result we get from predict function. So S is lambda. Yeah, so now that we want to optimize lambda, so we just estimated lambda, but we don't know which one is the best. And we can set seed for that. And then we do validation approach. So training set and the test set. Maybe later that we do cross validation also. For random observations, a random sample, just cross validation works fine. But sometimes the test and the validation approach is necessary. For example, time series data, we cannot randomly choose the points because time structure will be broken. So in such a case, still we need training set and test set. So validation approach. So first we try validation approach. We set the training set. Remember that in total we have 263 observations. So half of them we make it as training set, and the test set is just the complement of this. So we can say the negative train. So the test set is complement of train. Then yeah, we can evaluate the mean size of error. So mean of so test set. So we have response variable as y. So y dot test is just the test set for the y for test set. And yeah. Yeah, so now that we fit the rich regression and we see the error size. So maybe we set S is equal to 100. So we set, for example, the rich predict is equal to predict rich model, and the lambda is 100, and the data set that we should say the new X is equal to X and the test. So we pick up the training set. So the predictors for test set. Test is not found. The test was lowercase. Sorry. Then this. Okay, so then we can calculate the residual sum of squares. Maybe test residual sum of squares. Maybe test RSE. MSE y dot test minus rich dot pred, and that should work fine. And we take square the difference, so we put the square here, then take the average, then we get this. So RMSE, the test RMSE, test residual sum of square is the 113,000. If we do repeat this for all lambdas, then we can compare it. but here I will use the cross validation this time, and the cross validation we can use the cv.glmnet function and xy, and alpha is equal to 0. Again, alpha is equal to 0 means rich regression, and alpha is equal to 1 means the lasso here. So yeah, then we can see the size of the cross-validated mean square error as this. So I think that here is the point that the cross-validated mean square error is smallest. So log of lambda is about maybe 3.5. So that means the lambda is e to the power 3.5, like 20 or 30. Here, I'm not exactly sure what this means. Mean square error is actually much larger, probably. Yeah, I'm not exactly sure. Maybe it takes some value from maybe one standard deviation from this point or something like that. So sometimes if root mean square error does not improve much when the lambda gets smaller. I mean, the model gets complicated, more complicated, but the error gets not much smaller, then we stop somewhere. So this represents the sum rule. So basically, this is the best point. Maybe possibly you choose the lambda between here and here. So what's the best lambda, in fact? That we can get the cv.out $ lambda mean. Then we get the lambda, which minimize the cross-validated mean square error. That is 25.52. So exponential, maybe we can take the log of 25.5, 3.3, 3.24. So that is indicated in the previous figure. Here you can see this is probably 3.23. Yeah, so that's it for now. And they tried many different values of lambda. So so this is 100. So this is the index of observations for which the cross-validated error is minimized. So I don't know, probably they tried 100 observations, 100 values of lambda, and this is the one that we maybe cv.out cvm, we can say 100. So I think it has some problem. So they tried several values of lambda, 100 different values of lambda, but actually even the last one, yeah, actually the last one is the best. So that means the even smaller lambda may be better. So I'm not exactly sure to change this range. You can manually do that, right? So that we have the grid search for lambda. So yeah, I think the cv.glmnet function, that this has some options to choose the range for lambda. So lambda value, so lambda option in cv.glmnet. So we can modify that. Yeah. but probably it's almost flat. So maybe we just assume that this is enough. You can choose you can put the lambda option. Lambda is equal to sequence of lambda values. Then that we can see, we can calculate the cross-validated RM mean square error for different lambdas. Yeah, so yeah, that's the way to go, and we can get this is the cross-validated error, so 113,880. So yeah, actually, but the cross-validate, this is test errors. I'm not exactly sure. 1132, yeah, possibly maybe smaller lambda is sorry, the large smaller lambda may be better. Yeah, smaller lambda may be better. So maybe we can try that this time. So CV lambda. So smallest lambda is what? I'm not exactly sure here, but the smallest lambda 25, right? So 25. So lambda, maybe we can try maybe 1, 2, 5, 10, 20, and 25 maybe. Then here, 1, 1, 1. So these are the values, the CV cross-validated one corresponding to these 5 values, 6 values. So 1, 1, 2, 1, 1, 1, 1, 1, 1, 4, 5. So this is smallest actually. So maybe lambda is equal to 5 is maybe even better than lambda is equal to 25. Yeah, almost the same, but maybe here, maybe which one? The 1, 2, 3, third one. Maybe here, lambda, sorry, the third smallest one. So that means the third smallest one. So this one has the smallest, the mean square error, maybe. Okay, so that means we get this as the best model. So maybe we define the best rich model, the rich B, as GLMnet of XY, XY, and lambda, sorry, the alpha is equal to 0. This is rich regression, and lambda is equal to B, maybe 5. Yeah. Lambda is equal to 5. Yeah, then this is the rich. And we can get the coefficient for rich regression here. So these are estimated coefficients. So this is the best in terms of cross-validated value. So yeah, I don't know. I don't know how different this compared to linear regression. Linear regression, y, x, 163.1, negative 1.998. So yeah, actually slightly smaller. So rich regression hopefully works better for test data set. Yeah, so this is how to fit the rich regression. Next one, do you have any questions so far? Yeah. For training error, the always linear model is better in terms of RMSE. So MSE is basically, criterion for least square. So if you use least square and think about training error, the least square model always performs better. If you use rich or lasso, it gets worse. But the test error, possibly lasso or rich performs better. And the next one is lasso. So we don't really have difference between Lasso and Rich in terms of coding. Only the difference is the alpha value. Just use the GLM net. Maybe we use just training set. And also training set here. Then alpha is equal to 1. This is Lasso. And we also try several the values for lambda.
Professor?
Yeah.
Do you need to add a comma after train and Y?
X, the training set is the matrix, so we need the comma. X is a matrix, so we have the 2 indices. And Y is just a vector, so we have 1 index, so we shouldn't put comma. Then we get this here, L1 norm. So this is the actually L1 norm. So rich regression, I think it should say L2 norm. I don't know why this kind of irregularity happens. Maybe some rounding problem or something. But just the point is that so lambda is smaller. That means the on right hand side coefficient is larger. Lambda is larger, coefficient gets smaller. So of course the summation of the coefficient, absolute coefficient, gets also smaller. So that's the way to go. Okay, so now that we do cross validation, so maybe just to replicate the result that we set the seed. And cross validation for Lasso, cv.glmnet, x, y, alpha is equal to 1. Then plot cv.lasso. Now it works a little better. So this is the best one. Probably this is the maybe possible range. Maybe from here to here, root mean square gets slightly worse, but not significantly worse. So this is the optimal point. Log of lambda is about 0.5. So lambda value is about maybe 1.7, 1.8. And you can specify the best lambda value as the cv.las and which lambda mean. And the best value is 1.84. And which index gives the best lambda? Then that is 54. So they tried maybe 100 different lambdas, then the 54th one is the best. Then we got cross-validated the Lasso CVM. So this is the CV error minimum. Then this is 113581. So for rich regression model, that was 1114 or something. So probably for this data set, rich model, rich regression works better. Yeah, coefficient you can get in the same way. So just you can use the GLM net model again with lambda. So so maybe the best Lasso model is the GLM net xy alpha is equal to 1 lambda b lambda best lambda, then coefficient of Lasso b. Then we get the estimated coefficients. And you can see the more estimates are equal to 0. So this one 0, 0, 0, 0, at least 4 zeros. It wasn't the case for this rich regression. So coefficients are not necessarily larger. not necessarily larger, but all coefficients are non-zero. So Lasso estimated coefficients are more likely to be zero. For example, runs. Originally, in a rich regression, the coefficient is negative 0.19, but the small coefficient shrinks to zero in Lasso model. Also, maybe CAT bat, CAT bat. Oh, CAT bat actually does not shrink, but yeah. Yeah, so this is how it works. And alpha, why we say alpha is equal to 0 and 1? Probably we can fit the model with the alpha between 0 and 1, like 0.5. Yeah, so you can see that we penalize the sum of absolute value of beta j to the first power or second power. First power Lasso, second power the rich regression. Sometimes the people choose the somewhere in between 1 and 2. So basically alpha is basically, sorry, the 1, maybe 2 minus alpha. 2 minus alpha is the, the penalty term. So in this G-eliminate function, penalty is summation of beta j absolute value to the power 2 minus alpha. So if alpha is 0.5, we penalize beta j to the power 1.5. So that is possible. But practically, usually, if you try these two models, that's fine. If we optimize alpha value, probably that doesn't really matter. And outside of 1 and 2, alpha is equal to negative or more than 1. I think that we have some identification problem. So the parameter cannot be estimated in a good way. So maybe some identification problem, some computational problem there. Yep. Yeah. I think at least the less than 1, penalty is less than 1, we have trouble. Alpha is more than 1, we have trouble. Alpha is less than 0, possibly we can do that. I haven't seen it, but basically people are not really interested in it because practically it does not improve the model performance. The ESA textbook, the ESL mentioned about that. Okay, do you have any questions? Maybe we can do some practice next time. Okay, so that's it for today. If you don't have any questions, see you on Thursday. Otherwise, you can stay to ask questions. Okay, see you on Thursday.
Bye.
Good evening.
Thank you, Professor. Bye.
Bye.